Okay, this is the 49th lecture on resistance terminated LC ladder. We started this yesterday and we continue this today. The problem that we were discussing is that we want to realize an LC2 port in the form of a ladder which is terminated in a resistance R. The voltage across this is V2, the current is I2 and is driven by a source which could be a voltage source or could be a current source, one of the two. And therefore, the the transfer functions would be either a transfer impedance or a transfer admittance Y21. Z21 is V2 by I1, that is the input is now a current source and the output is a voltage. Y21 is I2 by V1, that is the input is a voltage source, the output is the current through the resistance, and these can be expressed. We also normalize capital R to 1 ohm because we know how to scale element values. If R is 1 K, then correspondingly we increase every inductance and we decrease every capacitance. Okay. So, we normalize capital R to 1 ohm. Under that condition, the transfer impedance Z21 can be expressed in terms of the Z parameters of the LC2 port as Z21 by Z22 plus 1. This 1 comes because of the normalized resistance, normalized load of 1 ohm. If it was not 1 ohm, it would have come Z22 plus R. That is the simplification. Similarly, Y21 can be expressed in terms of the 2 port parameters of the LC network, admittance parameters, Y21 divided by Y22 plus 1. If this R was not 1 ohm, then this would have been G, that is 1 by R. That is the only difference. We argued yesterday that because LC parameters are odd, because Z21 is odd, so is Y21, these are odd functions. Therefore, if either of them is given as P of S by Q of S, then the numerator polynomial P of S must be either purely even or purely odd. This must be either purely even or purely odd. And therefore, if the problem, to be specific, let us say is capital Z21, if the problem is to synthesize the given P of S by Q of S in the form of an LC ladder terminated in a resistance, then what we do is the given P of S has to be either purely even or purely odd. We break up Q into its even part and odd part, and then we argue like this, that if P of S is even, then we divide both numerator and denominator by the odd part of the denominator. That is, we identify Z21 as P divided by N, and then in the denominator we get 1 plus M by N, and therefore Z22 is identified as M by N. Z22, we argued yesterday that it is an LC driving point impedance because it is the ratio of the even to odd parts of a Hurwitz polynomial, all right. And therefore, the problem now, the problem of synthesis then resolves to the following, that is, synthesize the driving point impedance Z22 in such a manner that the zeros of Z21, which are the zeros of P, are realized, because they have the same poles and an N. Realizing Z22 shall mean that we have also realized the poles of Z21. The only care that we have to exercise is to see that the zeros of Z21, which are the zeros of P, which are in turn the transmission zeros of the network, are realized, such that transmission zeros are realized. This is the strategy. What we have said about Z21 also applies to capital Y21, exactly the same procedure. It would be exactly the same procedure. In case P of S is odd, if this is odd, then Z21 would be P divided by m, that is, you shall divide the numerator and denominator by the even part of the denominator, so that this becomes an odd function, and then this would be z22 would be n by m. We have indicated the odd case with black and the even case with pink. All right, and we started illustrating this by means of an example. The example that we took was, first example that we took was z21 is equal to 2 divided by s cubed plus 3s squared plus 4s plus 2. This was the example. And you notice that if we write this as P of s by Q of s, then P of s is purely even, and therefore you identify small z21 as 2 divided by the odd part of the denominator, that is s cubed plus 4s. All right, and you identify z22 as the even part, 3s square plus 2 divided by s cubed plus 4s. Is this okay? And the problem now is to realize z22 in such a manner that the transmission zeros are realized. The transmission zeros, if you look at this function or this function, are 3 in number, and they are all at infinity. 3 transmission zeros at infinity. And we have now to guess the structure as to how 3 transmission zeros can be realized. Obviously, if there are transmission zeros at infinity, then it shall be either a series inductance or a shunt capacitance. In a ladder network, it shall be either a series inductance or a shunt capacitance. And we argued that in this case, in order to realize 3 transmission zeros, our structure must be of this form: 2 capacitors and 1 inductor. This is what we want: 2 capacitors and 1 inductor. It could not be 2 inductors and 1 capacitor, because the driving source is a current generator. Okay? For current generator, anything in series is ineffective, and therefore this is the structure. And all that you have to realize now is that this impedance, the impedance looking to the right from port number 2, should be equal to Z22 with port number 1 open, and therefore
it could have been 3 capacitors in series.
3 capacitors in series is equivalent to 1 capacitor, and therefore they do not realize 3 transmissions here, they realize only 1. There must be an isolation between the capacitors. Okay? Now, what I was saying is, all that you have to do now is to realize this function in this particular form, and you see that this is a cover 1 structure, and therefore it can be mechanized by continued fraction expansion starting with the highest powers. Now, you cannot start continued fraction expansion of Z22 because Z22 does not have a pole at infinity, and therefore you have to start continued fraction expansion of 1 by Z22. Is 1 by Z22 Y22? No. That's right.
So why don't we start make this a covered 2 capacitors?
No, covered 2. Covered 2 will come capacitors in series. We want capacitors in shunt. Therefore, 1 by Z22, which is equal to S cubed plus 4S divided by 3S squared plus 2, we make a continued fraction expansion of this S cubed plus 4S, and you see S by 3. This is, the dimension is an admittance. Okay? And therefore, the first capacitor would be equal to 1/3. Okay? First capacitor will be 1/3. Then we have S cubed plus 2 by 3S. This is, pardon me, 10 by 3S. This divides 3S square plus 2, 9 by 10S, and this is an impedance. Therefore, the next inductor would be 9 by 10. Let us go ahead and draw it. 9 by 10S, this gives me 3S squared. I am left with 2 divides 10 by 3S. So, I have 6 by 10. I am sorry, 5 by 3, that is correct, 5 by 3s, and this is an admittance. So, 10 by 3s admittance 0, which corresponds to open circuit. It has to be, there is no other way, and therefore, the next capacitor is again 5 by 3 and the circuit is complete. All that we have to do now to complete this circuit is to add this 1 ohm resistance here. This is my V2 and the current generator here I1. This is the complete synthesis of the given specification.
So what will be cover 2?
Cover 2 concentrates on poles at the origin. The structure here, this is the structure dictated by the transmission zeros. I could have expanded Z22 in cover 2 or even Foster 1, Foster 2, no problem. But in order to realize transmission zeros at infinity, I do need this structure. I cannot do it with cover 1. I am sorry, cover 2.
So the capacitors could have been on the other side of the circuit.
Capacitors could have been what?
Exchange.
Oh, these two capacitors could have been on the other side. These two could be exchanged. No,
So value.
no, that will change the Z22. It will not keep Z22 the same. Z22 with these two exchange will be quite different. The coefficients will be different. Any other question?
So then how do you know the order? Like earlier when we did this expansion, then we did it from...
We went from left to right. Here we are expanding Z22. Z22 is measured from port number 2. So you go back. You must be careful in this. Okay. We are not developing Z11. We are developing Z22. And the last element, there are saving features that I mean, it's a kind of automatic error correction system, automatic control system, that unless the last admittance is 0, it will not come as open. The last element must come in shunt because your input source is a current generator. These are all automatic correction mechanisms. If it does not come, then you suspect that something is wrong. All right. Let us take the second example. Let us say the other extreme, that is all the 3 transmission zeros, let us say, are at the origin. That is example 2, let us say Z21 is equal to S cubed divided by the same example, S cubed plus 3S square plus 4S plus 2. All the 3 transmission zeros are at the origin, right? None at infinity, and therefore cover 2 shall now be appropriate. Okay. Let us see, the numerator is odd, and therefore your Z21 would be S cubed divided by 3S square plus 2, and Z22 would now be S cubed plus 4S divided by 3S square plus 2. Okay. Now the structure that I want is transmission zeros at the origin, and therefore I want a series capacitor and 2 shunt inductors, 1 and 2. This is what I want. This is what I want to be Z22. Agreed? You have to guess this structure. 3 transmission zeros all at the origin. So series impedance pole, 1 capacitor and 2 inductor. It could not be 2 capacitors and 1 inductor.
So you said the transmission zeros of Z22 should be the transmission zeros of Z21.
No, no. There is no transmission zero of Z22. Z22 is a driving point function. Okay. You have to develop Z22 in such a manner that the zeros of Z21 are realized. Zeros of Z21 are the same as transmission zeros. Okay. And
If it was S square,
pardon me,
if it was S square.
we will come to S squared also. If it was S squared, then 2 zeros at the origin and 1 at infinity. We will do that example also. In fact, we will do for S to the 4th also. All right. We will do that. Now, so what do? I expand Z22 in cover 2. Z22 does not have a pole at the origin, therefore I must take the reciprocal of this. All right. I must take the reciprocal of this. 1 by Z22 is equal to, now I write as cover 2 means continued fraction expansion starting with the lowest power. So 4S plus S cube, let us do that, 2 plus 3s squared, the what is this? 1 by 2s, correct. And this is an y, this is an admittance. Is 1 by 2s all right? Yes, this is all right. 2 plus s squared by 2. This is an admittance, so the first inductor, this must be 1 by SL, this is 2, agreed? Next, 3 times 2, 6 minus 1, so 5 by 2 s squared, is that correct? 6 minus 1, right. 4s plus s cubed, and I shall have here 8 by 5s, is that correct? This is a z, and therefore the next capacitor is 5 by 8, 1 by sc, okay. 4s, then I am left with s cubed and 5 by 2 s squared, so 5 by 2s, 5 by 2s squared, 0, this is an admittance y, and therefore the next inductor is 2 by 5, and there is a 0 of admittance, so this must be open, all right. This is Z22, and all that I have to do to complete the network is to add this 1 ohm resistance here and the current generator here. The network is complete. This is indeed a high pass filter. It is a high pass filter. All transmission zeros are at the origin. What is the infinite frequency response of this network? Common sense, look at the network and
It's a 1.
1. Infinite frequency, this is open, this is open, this is open, this is short, so the total current goes, and since it is 1 ohm, so V2 is equal to I1, alright, so it is 1.
So if we had started with Y21, would we have gotten a different circuit?
You would have got a different circuit surely. We will do that. To bring variety into experience, let us take an admittance now, let us say Y21, third example, and we take his case, that is s squared, or shall we take s, whatever you like, s squared is okay, s cubed plus 3s squared plus 4s plus 2. I will not complete the example, I will indicate how to, well let us complete, okay, one we will complete, then we will leave things unsettled for you to settle. Since this is even, therefore this is to be y21 divided by y22 plus 1, agreed. So y21 shall now be s squared divided by s cubed plus 4s, agreed, and y22 shall be 3s squared plus 2 divided by s cubed plus 4s. Now I argue what kind of structure. First you have to decide on the structure. The structure is 2 transmission zeros at the origin. Now obviously I require one inductor in shunt, okay, and a capacitor in series,
So but how we cancel the s out from the numerator and denominator plus Y21? So
Well, that does not change the transmission zeros. Transmission zeros are of capital Y21. We can do that, but that does not settle the transmission zero, that does not change the transmission zero.
How there are two transmission zeros?
Look at Y21, there is an s squared factor here, so 2 transmission zeros at the origin and 1 at infinity, s squared by s cubed, alright, and 2 transmission zeros at the origin, we require an inductor in shunt and a capacitor in series. We also have a transmission zero at infinity, and to take care of that obviously we require an inductor in series. So we shall have indeed an inductor in series, okay.
So but now there is a current source and
There is not a current, it is not a current source now, it is a voltage source because it is Y21, Y21 is I2 by V1. I was expecting this question, how come the last element is in series? Because it is a current generator, and you see you will develop now Y22, you will develop Y22, which means that this should be Y22 under the condition that this terminal is shorted to this terminal, isn't that right? Is this clear? This terminal, because it's a voltage generator, so when you measure Y22 you short circuit this. Okay, so Y22 would come under the condition that this is shorted.
Excuse me, what will happen if we have the parallel inductor first, then a capacitor in series, then an inductor in series?
Say it again.
A parallel inductor first.
Parallel inductor, what does that parallel inductor mean?
So looking from there.
Looking from this side.
Yes, so if we have first an inductance in parallel.
Okay,
then
in shunt, right? Then
and then a capacitor in series.
Series.
Then an inductor in series.
then an inductor in series. Well, this will not do the job because there is a voltage generator here. This inductor will therefore be ineffective.
So how we got the second inductor?
Oh, this is to take care of the transmission 0 at s equal to infinity.
Third transmission.
Third transmission 0. So there is a voltage generator and this inductor in series will cause a transmission 0.
So can we interchange the parallel inductor and the capacitor?
Can we interchange this and this? That means can we have an inductor here?
Yes.
No. That's an interesting question. Let's do this. What Soumya suggests is this. Is this what you are suggesting? Okay. Now
Current output is to be measured, and that will be
current output is to be measured, so it doesn't matter. We have a voltage source here.
So
Will
capacitor
this-
is ineffective.
Pardon me?
So capacitor is ineffective if you are measuring current.
Why? No, the current here will be affected by the capacitor. That's not the point. There is something else.
So now when we short this,
No, wait a second. There is more fundamental and more common sense.
The alternate,
Pardon me?
the alternate LNC.
No, this I claim
Yes, sir.
does not.
only two transitions.
That is correct.
Only two transitions.
Absolutely wonderful. This is the correct thing. Only two transmissions. Why?
So when it's equal to 0, then they will share.
Because if you look here, the Thevenin equivalent is simply a constant multiplied by this V1 in series with an inductance, and therefore one transmission 0 to infinity and one at the origin. That's all. Third one is not realized. You have to be very careful. You have to be very careful in this. So this is not admissible. All that you have to do now is to realize this structure. Okay. So what we have is y22 equal to 3s square plus 2 divided by s cubed plus 4s. This is what you have to realize. In the form, first an inductor, then a series L and C, and y22 shall be realized when this is shorted. Okay. So what do? We first take out the pole at the origin of y22. All right. It can also be looked upon as cover 2, but just one step, so why bother? So what we do is we write y22 as what is the residue at the origin? Isn't it 1 over 2s? Correct? When s tends to 0, it is 1 over 2s. So what is this inductor then? 2 Henry. Agreed? Plus some admittance y1. Let's see what y1 is. y1 equal to 3s square plus 2 divided by s cubed plus 4s minus 1 over 2s, which is equal to 2 s cube plus 4s. All right. Then 6s square plus 4 minus s square minus 4. Is that okay? My simplification. 4 and 4 cancel, so it is
5s square plus 2.
it is 5 by 2
Only
5s divided by 2
s square.
s square plus 4. Agreed? This I can write as, let's go ahead with the synthesis. I can write this as 2s by 5 plus 8 by 5s. Agree? Now since this is an admittance, reciprocal, this should be an impedance, and obviously L and C, the other L and C are obvious now. What are they? The inductance is 2 by 5 and the capacitance is 5 by 8. So the total network shall now be add this resistance 1 ohm, remove this short circuit and add the voltage generator V1. That is it. This takes care of the transmission 0 at infinity, this at the origin and this at the origin. 2 transmission zeros at the origin and 1 at infinity. What kind of a filter is this? Band pass, that is correct. It is also obvious that when these two resonate, the total voltage appears across this, correct. This becomes a short circuit only at the resonance frequency. At 0 it is 0, at infinity it is 0, in between it has a maximum and therefore it is a band pass filter. Let us take the another variation of this. Example 4. Suppose y21 is s divided by the same denominator, s cube plus 3s square plus 4s plus 2. Then my y21 shall be s divided by 3s square plus 2 and y22 shall be s cubed plus 4s divided by 3s square plus 2. Alright. We have divided both numerator and denominator by the even part of the denominator. Now how many zeros are there at the origin? 1 transmission 0 at s equal to 0 and 2 transmission zeros at s equal to infinity. So what is the structure? 1 transmission 0 at s equal to 0 can be taken care of by shunt inductance, or do you like a series capacitance? Series capacitance, alright. Then what? 2 transmission zeros at s equal to infinity, how do you take care of that?
Shunt inductors.
2 shunt inductors.
It's a parallel inductance. Shunt inductance is series.
Shunt inductance does not give a transmission zero.
Series shunt capacitance and the series inductance.
Shunt capacitance and a series inductance. Okay, where would you put the capacitance? Here?
First series. First series inductance.
First series in here.
Yes.
Okay, then
Yes.
a capacitor. Will this do the job? This takes care of transmission 0 at infinity. This takes care of transmission 0 at infinity because there is a 1 ohm resistance here. And this takes care of the transmission 0 at the origin. This is a perfectly valid synthesis. Absolutely wonderful. All that we have to do now is to add this 1 ohm and add the voltage generator here. But how do you synthesize now? All that you have to do is first to remove the pole at infinity of y22. Can you tell me what this value shall be? 1 by 3, that is correct. And if you remove this pole at infinity, all that remains shall take care of this series resonance circuit. And I can do it by inspection. You see, if I remove this, what shall remain? If I remove s by 3. Well, I will leave that as an exercise. I will not complete this, okay. You understand what you have to do. Alright, now let us take example 5, another variation. Suppose Z21, yeah. Direction of current is always 2 port, always going in. Always going in. That is how the parameters are defined. Okay, now suppose it is s to the 4th divided by s cubed plus 3s squared plus 4s plus 2. Okay. Now therefore my Z21 is equal to s to the 4th divided by s cubed plus 4s, and Z22 would be equal to, pardon me, 3s squared plus 2 divided by s cubed plus 4s. How many transmission zeros now? 4 transmission zeros at the origin. right? None at infinity. Now, there is a fundamental contradiction here. There is a fundamental principle that is being violated. Unless you realize this, you will end up in a network, all right, but that network will not realize what you are wanting to realize. The claim now that I make is that this function is not, repeat, not realizable by an LC ladder terminated in a resistance. I make this assertion, either you justify or counter.
So degree of denominator.
Degree of denominator is 3, degree of numerator is 4. Pardon me? Poles are not on j omega, it cannot be on j omega axis. It is a Hurwitz polynomial. This is a Hurwitz polynomial. Well, these poles are on the j omega axis. S times s square plus 4. Yes, one is the origin, one is plus minus j. Any other? Where are the poles of Z22? S equal to 0 and plus minus j2. Where are the poles of Z21?
Minus 4.
Infinity.
There is a pole at infinity. Can Z21 have a pole which is not shared by Z22? No, it cannot have a pole which is not shared, and therefore the degree of the numerator here cannot exceed the degree of the denominator. So this function is not realizable by an LC ladder terminated in the network, terminated in a resistance.
Sir, can Z21 have a pole in right of plane?
Can it have a pole in the right hand plane? No network function can have a pole in the right.
When the numerator is s raised to the power 4, then and there we can say that it's not realizable.
That is correct. That's what I am saying. No, it doesn't make a pole in the right hand plane. It makes a pole at infinity. Transfer function can have a simple pole at infinity. But in this case it cannot have, because we are realizing in terms of two z parameters, and any pole of Z21 must also belong to Z22 as well as Z11. The pole at infinity here does not belong to Z22. Z22 at infinity is 0, and therefore there is a contradiction. So this function is not realizable. Point clear? Okay. This is one method of synthesis. We will take one example in the problem session of synthesis of resistance terminated ladder, but the caution that I want you to exercise is, please pay attention to whether it is a Z21 or Y21. That is, whether the last element that you develop will be in series or in shunt. If it is a current generator, that is, if it is a Z21, then the last element must come in shunt, whereas if it is Y21, the last element must come in series. Okay, this is.
Output will be taken across the.
Say it again.
Output will be the current.
In Y21 the output is current, in Z21 the output is voltage. Okay, right. Now this is one method of synthesis. Let us look at some other elementary methods of synthesis. Suppose you have a transfer function V2 by V1. Suppose this is to be synthesized, a T of S, a voltage transfer function V2 by V1. And suppose it is very complicated, maybe of this form, let us say S minus 1 by S plus 1 half multiplied by, let us say, S squared minus 2S plus 2, S squared plus 2S plus 2. Where are the poles? Complex, right? I want it that way. Okay. Multiplied by, let us say, something else. It is a very complicated function, but
Non-minimum.
pardon me?
This is non-minimum.
This is non-minimum phase. Yes. How do you know it is non-minimum phase? Because there is a 0 at plus 1. This also gives zeros in the right half plane. And do you realize that this is also an all-pass function? This is also an all-pass function. What is an all-pass function? If the denominator is q of s, then the numerator must be q of minus s. That is right. So this is also an all-pass function. Suppose, for example, this is what we wish to realize. Now obviously the realization would be very simple if we could realize these transfer functions individually and could multiply them. This is like achieving a gain of 1000. You can have an amplifier first stage of gain 100 and the next one 10, provided they do not load each other. That is, when the second stage is cascaded to the first, it does not load. In other words, it does not reduce the gain. Now a situation like this can be thought of here. Suppose we have two networks cascaded such that the first one realizes this, the second one realizes this. Unfortunately, however, with passive networks a buffering is not possible. With an active network, well, if the input with op amps, for example, input impedance of an op amp is infinity. So if you cascade an op amp to anything, it does not load. But unfortunately in passive networks there is no such buffer. But the saving grace is there are networks which are called constant resistance networks, which can perform this job of cascading. And the idea is this: a constant resistance network is defined as one which, when terminated in a resistance R, gives an input resistance of R, and vice versa. That is, if it is terminated at this side, the same network, if it is terminated here with the same resistance R, it again gives a resistance R. This is the definition of a constant resistance network. It has to be, we are considering only reciprocal networks. This does not give reciprocity, no. Reciprocity is something else. That is, the generator, cause and effect have to be interchanged. It is not a question of reciprocity. We assume that n is reciprocal. Now can you make a conclusion about the character of n? If this is so, that is, if when terminated at port number 2, port 1 presents a resistance R, the same resistance R, and if it is repeated, that is, if port 1 is terminated in resistance R, it gives resistance R at port 2, can you decide something about the character of the network? Pardon me? That is correct. It is symmetrical. No, bilateral, let's clear this. Do not make this mistake. Bilateral is a two-terminal element. Bilateral refers to a two-terminal element, that is, current passes equally well in both directions. On the other hand, if a network contains only bilateral elements, then it is called reciprocal. Okay? Reciprocity is understood. We assume that all networks that we are considering are passive, linear, time invariant and reciprocal. All right. Now this gives the character that constant resistance networks must be symmetrical. Okay. Now suppose two such networks are cascaded, two such constant resistance networks. That is, if I have a resistance R here, then what is the resistance here? Again R, and therefore the transfer function of this network with a termination of R is not disturbed. In other words, N1 could realize this and N2 could realize this. The input impedance here shall again be R. Agreed? So in fact what we can do is N1, by N1 we realize S minus 1 by S plus 1. By N2 we realize S squared minus 2S plus 2 divided by S squared plus 2S plus 2. And to achieve the factor of half, what we do is we drive it by a source of internal resistance R. All right. Then what is the voltage here? Half of V1. So the factor half is realized. Do you understand the importance of constant resistance networks? That if we have constant resistance networks, then we can realize a complicated transfer function by decomposing it into simpler ones, and the synthesis in most of the cases is obvious just by inspection. Okay, let me give you an example of a constant resistance network. One example, constant R network. The lattice is an example of a constant resistance network. Let's have a lattice with series element ZA and shunt element ZB. As you know, lattice networks usually are symmetrical, and therefore we usually don't draw all the 4 elements. What we do is we put a dot here and we put a dot here. This means that this cross element is also ZB and this series element is also ZA. Alright. Is the point clear? This is a nomenclature so that you don't have to draw all the 4 elements all the time. If this is to be a constant resistance network, it is a symmetrical network, then that is the first sign of constant resistance network. It has to be symmetrical. All right. Okay. If this is terminated in R, then what we want is that this should also be R. That is what we want, right? If it is to be a constant resistance network. Now we can work in terms of Z parameters or Y parameters. You know that Z11 and Z22 of this network is simply ZB plus ZA divided by 2, and Z12 is equal to Z21 is equal to ZB minus ZA divided by 2. All right. Now you also know that the transfer function, well, you recall that this is a folded version of a bridge network that we demonstrated yesterday. Okay. Anyway, you also know that if a 2-port is terminated in the resistance R, can you find out the input impedance in terms of the Z parameters? The input impedance is, we have shown this earlier, it is Z11 minus Z21 squared divided by Z22 plus R. This is the input impedance. Can you prove this? Very simple. How do you do that?
So T network with Z11 minus Z12.
Okay, you can use a T equivalent because the mathematical equivalence. You are not replacing it by a physical network, and then you can find this out. Or you can go back to the roots. V1 equal to I1, Z11, etc., etc., and then you write V2 is equal to minus I2R. Okay. Now if I substitute these values. If I substitute the values of Z, well, what is Z22? Z22 is the same as Z11. Now, if I substitute these values here and simplify, the simplification takes a bit of time, you will see that Z in equal to R implies, pardon me?
So Z is equal to R square.
That's right, implies that the product should be equal to R square. This is the condition for constant resistance networks. Okay, ZA ZB equal to R square. In other words, such networks, such impedances, well, let me introduce a term, such impedances which when multiplied with each other gives a constant are called, no, I would not use that term. It's not a very appropriate term. I was hesitating. They are called complementary. It's not a very appropriate term. So forget about it. The the question is that ZAZB equal to us. This is the condition. Under this condition, the, let us say this is the lattice where ZAZB is equal to R squared. If it is terminated in R and if it is driven by a voltage source, okay, it can be shown that V2 by V1 is equal to R minus ZA divided by R plus ZA. This also I will leave to you. I will not do the algebra. You can show. How do you show this?
V2 by V1 is Z equivalent, Z11 by Z.
No,
Z12 by Z11.
no, it is not, because there is a termination R.
So equivalent parameter we find out.
You find out the equivalent parameters and then decide this. But I am serious in asking you to do this. Okay, please do verify that this is so. Can you write this in terms of ZB instead of ZA?
Yes, sir.
Yes, because ZA is this, you can show that this is equal to ZB minus R divided by ZB plus R. Okay. So that if the parameter, if the function is s minus 1 by s plus 1, all that you require is ZB should be an inductor of value 1 and R should be 1. What is ZA then?
1 capacitor.
A capacitor of value 1 farad. It is obvious by inspection. Similarly, if your function was s squared minus 2s plus 2 divided by s squared plus 2s plus 2, what would be your ZB and what would be your ZA? Would you believe ZB would be s squared plus 2 divided by 2s? Agreed? Which is a series combination of an inductor and a capacitor. And what would be ZA?
2s by s.
ZA would be simply the reciprocal of this, which means a parallel combination of inductor and a capacitor. So, the synthesis, no other calculation is needed. It should be obvious by inspection. All right. We will do a few problems in the problem session.